Okay, great. Well, thank you for the introduction. My name is Brad Hayes. I'm a professor at the University of Colorado Boulder, and so today's talk is titled Explainable AI for Establishing Shared Expectations During Human-Robot Collaboration, but you could just as easily think of this as a talk for any kind of autonomous system interacting with any kind of person. So very briefly, if you went into my background, so I am an assistant professor of computer science at the University of Colorado Boulder, where I work on the intersection of AI and robotics with humans in the loop. I also work at a cybersecurity learning company called Circadence, and so I'm going to try to more or less cross boundaries in terms of applications of this explainable AI work. And in particular, my focus tends to be on explainable systems as the only responsible way to actually deploy AI or machine learning systems in the real world. So just a very brief bit about the company that I work for. So we develop cybersecurity automation technology. So not only do we do gamified learning, but we also then take that data, use it to train agents that can then go off and do tasks on your cyber infrastructure. So that means as we present people with screens like this in order to trick them into going to screens like this, and then tricking them with that into virtual machines where they actually learn how to do these kinds of either red hat or white hat activities, red team or blue team activities. So I think one thing that has come around that I've added since starting to talk to a bunch of people here is that it turns out you can do a PhD thesis. You can spend 6 years trying to build technology that people will want to use that will make the world a better place. But you do one thing on Twitter and people just zoom in on that. And so I'm most, I think, well known for making this Twitter bot that mocked Donald Trump during the 2016 election. And that's also kind of just followed me. And so it turns out that maybe one of the morals here is it doesn't actually make much of a difference what you think is important, because people latch onto something, and just because your system can speak out on the internet doesn't mean you should make it do that. And my favorite quote was this. Okay, so my real research focus is on collaborative human and robot interaction, where we're trying to use human-in-the-loop AI techniques to make people better at what they're doing, right? So if that's making them safer, more effective, more efficient, it's all fair game. And if you look at the current state of human-robot interaction, you get pictures like this, or as I like to frame it, happy people smiling with robots. And in this case, like, we see that none of this looks like the automation cages of old, right? So the cages have been replaced with algorithms, sensors, and human-robot interaction research. And I would argue in a lot of these cases, though, people are just coexisting with these systems. And that's impressive, right? We got the robots to not kill the people, but they're not necessarily collaborating with these systems, which is a completely different bar altogether. Now, it's worth mentioning, not everybody's super thrilled to be working with the robot, but to be fair, the robot is not super thrilled to be working with the person either. Now, when we first had this idea, right, of hey, we can automate these physical tasks, should we put these things in cages? No, we should just put these in factories, right? So people, when they were first given access to automation techniques, didn't see the need for any of this work on explainability. They assumed that people would just accommodate these systems. And they were right, except when things don't go exactly according to plan, bad stuff happens. And so this is an article showing a bunch of different industrial accidents that happened largely because these systems, these automation systems that interacted in environments where there were people, had no idea that there were people in those environments. They didn't have to model it. They didn't have to know what they were doing. And so the idea that these systems could then explain their behavior to a person is completely off of consideration. Okay, so anybody who's worked in robotics or any kind of automation knows that getting it to do anything useful is really difficult, right? So just getting a robot in isolation to be functional is like scaling a mountain. Once you add people into this, everything gets worse, right? If you've ever had to create a human interacting system, you'll know that people are generally the worst. They try to break your system, they push the boundaries, they make everything a lot harder. And in fact, I would argue that collaborating during task execution is more so resembled by this. And so this seems intractable, right? So worst case, we have this DEC-POM-DP, decentralized partially observable Markov decision process that might be unsolvable. If it is solvable, maybe our systems are completely unrelatable to people. And even still, even if they are, like, they might still be unsafe. So I wouldn't just come here and say this problem's impossible. So I would say that we can solve this by segmenting it into some fundamental components. And in fact, I would say that first we could split these desired criteria up and then try to solve them, as hinted at by the title of the talk, with establishing shared expectations. So if we can establish shared expectations over the low-level behaviors and the decision-making capability, then we could start to approach something that is resembling a collaborative system. Now, as a brief aside, Donald Michie proposed different criteria for machine learning. And so this weak criterion largely describes the systems that we have now. So this just says that as you get training data, your system changes in response to that, right? So that's the definition of a system that's learning. Now, he also proposed a strong criterion, which said that there has to be some kind of explicit symbolic update. You could think of that as saying that the model has to communicate back to you something about what's changed internally. Now, what's missing from this definition is that it's interpretable by a person. And that's why he also introduced the ultra-strong criterion. And so for the rest of this talk, we'll be addressing systems that fulfill this ultra-strong criterion. So this is just saying that all of the above things happen. So you have a system that changes in response to data. It has an explicit symbolic update. And most importantly, that update has to be expressed in a way that people understand. As a quick introduction to some other terminology, I'll just now try to use a neural network-based classifier or something basically resembling that and ask the audience, where is this? Does anybody know where this is? Who said it? Okay. But like, what is this a picture of? Okay, great. So I have my black box system. It's not, a neural network, but it's close. Except I have no idea how my classifier came to that description. Now, if I could ask my classifier a question, like, why did you say that's a factory? What would you say? So there are fixtures, there are these different things, and I'm getting features, right? My classifier is now explaining to me the features. And so I will say that that is a comprehensible classifier. Now, I have no idea what the relative importance of these features are. And it turns out that people are really bad at explaining that. So we're effective at defining the features we use to make decisions, but we're not as good at defining how we use them and what proportions related to each other. But if I could look into that system and see what those weights are, then I would say my system is interpretable. And now one of these does not imply the other, right? So I could have features that aren't really describable, but I could see how well they're being used, and vice versa. So we're going to focus on trying to make systems that are comprehensible and interpretable without throwing away all of the great machine learning advances that we've had over the last decade or so. And I would also try to isolate the importance, right, of being able to look into your model. So a pretty famous example, now this was intentionally created this way. This wasn't just some happenstance mistake, but a group of researchers created a classifier to detect if an image contained a wolf or a husky, right, or a dog. And so you just had two classes, and they trained this model on photos of wolves, photos of dogs, and it performed really well on the data set they had compiled. Then they took it into the real world, and it did terribly. And it was really unclear why until they developed some kind of introspection technique to highlight the pixels of their model, or the pixels related to the activations in their model. And they realized that they really didn't train a wolf versus husky classifier. They trained a snow versus not snow classifier, because all the photos of wolves had snow in the background, and that's a much more salient feature. So when we're trying to build these systems, again, these are the things that we're really looking out for. So the first topic I want to cover here is learning from demonstration. And so the reason why I want to cover that is because we're not very good at creating cost or reward functions, right? So that's why we have to go to demonstration, because demonstration implicitly encodes all of those common sense things that we generally forget to include. So a quick example of this, if we're trying to build some AI to do road navigation, we might want to encode that it takes the shortest amount of time to get us from point A to point B. But if we forget to encode that just because your physics simulator says you can go through somebody's fence, you probably shouldn't, you're going to get unintended consequences from your model. So with that in mind, I'd like to show a video. So this is a robot that's meant to help people build IKEA furniture. So it's able to watch what you're doing and then run summary statistics over segmentation of this task to figure out, oh, this person's taking too long. What can I do to help? Oh, I can hand them this part. I can give them this tool that they're missing. And when I showed this video at the end of my PhD, they did give me my degree, but what they didn't realize was that this system is incredibly dangerous. Why would anybody want to get in front of this robot, put their hands next to it, let alone working around these tools, right? Because the implicit assumption was that this system, which was trained from demonstration, was trained from expert demonstration. And the other person in this video was another PhD student in the lab who'd seen me working on this for a long time and had a great familiarity with how this system works. But if you have no idea how that system works, that's probably terrifying because you have no expectation of what's going to happen. And it turns out it really matters where your demonstrations come from. So this is a video of a garbage truck with a robot arm that's being teleoperated by somebody inside the cab there. Now, if I told you that that robot arm from the last video was being trained by this person, would you really want to go and work with that robot arm? Right? What would it take for you to want to go and work with that robot arm? So this is the question that we're really looking at. Anytime we have a system that learns, anytime we're trying to train a system, is did it really capture my intent? And so the next two topics I'm going to cover are going over methods that we can use to try to answer that question, to try to figure out if our autonomous system really captured our intent. So this first paper that I'm going to talk about briefly was published at IROS 2018, which is a robotics conference. And so this is a paper about augmenting a learning from demonstration system to make it more safe. So for those not as familiar, learning from demonstration systems typically work with 3 steps. So the first one is you record trajectories, right? So you get your demonstrations. Then you go through some kind of alignment step, and most people just hand wave this away, but this is also a really deep and difficult area. And then once you have an aligned data set, you want to do sub-goal discovery or find keyframes, right? So instead of having to solve the whole problem, you have a bunch of intermediate points along the way, and that makes everything much more tractable. Now, when you do all of this, you're assuming that your model is going to capture all of those things, those rules that make you not a sociopath, and that's actually quite difficult to do. And so it turns out that trajectory-based demonstrations, right, so direct demonstrations of a task are great. They have the lowest overhead in terms of translation to figure out your intent. Unfortunately, the information content is quite limited. You only get information about that narrow ledge of your state space that somebody gave you the demonstration on. And so anything like that we might consider common sense, like if you're going to carry a coffee cup, don't turn it upside down as you do it, that's not necessarily present, right? So your robot doesn't have common sense. Your autonomous system doesn't get any of that for free. And so we can say that, well, okay, what if I took a prohibitively large set of demonstrations to get that? Well, you probably don't have time to do it. And if somebody else spent the time and money to do that, you'd have to borrow it. And in which case, you probably still shouldn't trust it because how are you going to figure out that it actually has that common sense inside? So the thing that we propose in this paper is just adding constrained task and motion planning into the learning from demonstration paradigm. So the core, I guess, justification here is that natural language is really good at explaining broad classes of behavior, whereas demonstration is really good at being very explicit and specific. So you can say, don't turn the cup over. As you demonstrate something, and then you can attach that constraint. So even if your model is, going about it or wants to go about it any which way, having that constrained layer will prevent it from doing these kinds of bad things. So you could have a classifier that operates on your state space that just checks everything that your motion planner is sampling to say, okay, it's upright, that's good. It's upright, that's good. That's not upright. I'm going to reject that. I'm going to keep planning around it. And so it turns out that we can use narration as a surrogate, at least for common sense, right? So this is taking human annotation and then driving it into the system, and then encoding that as an immutable constraint over the task and motion planning space. And we get all kinds of great benefits from this. If you're a PhD student in my lab stuck doing robot demonstrations, then they're pleased to see that it only takes one annotated demonstration to correct a skill, as opposed to taking upwards of 30 or 35 to achieve not even as good results. But this notion, right, of dictating constraints so that you have some idea of what your system is capable of or explicitly not allowed to do is really important. And so now that we've published this, obviously we have collaborative robots everywhere. We solved it, and the world can thank us for it. Except that's still not the case. Even if we have constrained task and motion planning where we can annotate these things, we don't necessarily get that, because it turns out it still means a lot to know what's about to happen so that you can negotiate these kinds of interactions. So here we're doing a simple handover, or what should have been a simple handover. And you might see that the can is also punctured and spraying Diet Coke everywhere. And this is something that I imagine most people think of as a pretty straightforward behavior. Just handing something over. But as introductory students in robotics quickly learn, is that everything is difficult and nothing comes for free. So how do we get around this? How do we understand what these systems are about to do? So the last paper I want to talk about gets into this. So if you search for human-robot collaboration on Google image search, you get photos like this, where this person is doing something I would never recommend. They're putting their hand between a robot and a rigid body. That robot also has a metal gripper. And the only reason they're willing to do this is probably because either they programmed the robot, or more likely that robot's off. And so it turns out that anytime you're having some kind of safety critical teaming situation, you need communication, right? Communication is the missing link that allows us to actually do pretty much anything. And so if we look at the literature, there are a lot of great papers on short-term collaboration. But if we look at the longer term, like beyond 10 seconds, well, you just get a bunch of graphs. And the one on the top right is mine, so I'm guilty of this as well. But you can imagine if you had a really safety critical situation, these people are going to talk to each other. So what happens if we replace one of them with a robot? What happens then? Well, the robot can answer this question. They can say, okay, here's my state space, and these blue states are the ones where I drop the bar. So I should probably communicate that to my collaborator so they know under which circumstances I would drop this bar. So the question, though, is how do you communicate that? Well, if your robot just spits out state vectors, it turns out nobody's going to work with your robot because it doesn't mean anything. And if you have somebody who's working on the floor with your autonomous system, they don't get to see the design sheet or the code. And it's not even clear that if they did, they would be able to make any kind of sense of it. So here's how we make these opaque systems more understandable in 3 extremely computationally expensive steps. So the first one is we need to map queries down to regions of state space, right? So we're trying to answer that question of how does the robot give the human a theory of mind about the robot? And then once we have that, we have to generate our response. So we're going to summarize these state regions and communicate it back. And so the core idea here is borrowing from the planning community. So we have these Boolean classifiers. So these are just predicates. So A is on top of B, or the paint is drying, or the camera is powered. And it's helpful to think of these things as shapes covering a region of our state space. And so we can have questions like, when will you do a particular action, right? So then we need to isolate all the states where that action is the most likely one from our policy. Why didn't you stop in front of the door? That one's a little bit more tricky. But all of these questions, and then like, what do you do under certain conditions where we're defining a subgraph over the full state space to explain or summarize. All of these are just about mapping language down to regions of state space and then figuring out how to summarize those regions of state space back to somebody. So if we recall this visual analogy, right, we can formulate this as a set cover problem. So we just apply a Boolean algebra, so ands, ors, and negations, and solve that such that we can get a string of these classifiers to summarize a region of state space. So here's an example. We have our model, our graphical model of our policy down there on the bottom. I ask, when do you inspect the gear? So that's finding all the states where inspect gear is our most likely action. So let's say it's these three. Then we want to find the mapping, right, that covers those states. So if I had one at conveyor belt for the robot that covers these 8 states, and I have detected gear that's just true at these 5 states, then conveniently for this example at least, the intersection of those precisely covers the 3 that I'm looking for. And so then I can just use some string templates to formulate some kind of response back to the person to give an intuition for how this controller works. So with this, we can actually get some detailed introspection as long as we're asking the right questions. And so it turns out that explainable models aren't really enough. So asking, why didn't you inspect the gear? You'd want an explanation that has 3 core components. So fault diagnosis, a policy explanation, and a root cause analysis. And the takeaway here is that even though we can build interpretable and comprehensible systems, we can make algorithms that enable these kinds of explanations. These things don't enable explanations on their own. And so when, just to really quickly wrap up, we looked at this as a big problem because that requires a lot of expertise on the part of the person who's interacting with these systems. You still have to ask the right questions, right? So these interpretable machine learning models still require an expert interrogator. And so we did a real quick user study to see what happens when autonomous systems try to provide explanations to people and how useful those are. The details aren't as important. We made people play this really hard game called real-time color Sudoku. Imagine just filling out Sudoku with somebody across the table from you with no turns, except the robot's perfect at this game. And so it's really maddeningly frustrating. But fortunately, you were on the same team and the robot was there to help. So if the person was about to play a move that would lose the game for them, the robot stopped them in 2 of our experimental conditions. Right? So in one of them, the robot said, hey, if you do that, you're going to lose the game. Don't do that. And in the other one, it explained why. And so we came up with all these hypotheses, and we thought that people would find the robot more helpful and more intelligent if it helped them out. And it turned out people only thought the robot was more helpful when it justified itself. So that was a little odd. And then we looked at our objective hypothesis that people would complete the game faster if the robot explained itself and justified its recommendation. And we couldn't test that hypothesis because pretty much nobody listened to the robot if it didn't justify itself. So there's more to it than just an explanation, right? We also have to come up with systems that are able to convince people that their recommendations are correct or that their own analyses are correct. And so with that, I will conclude and thank you for your time.